In decaying turbulence, energy appears to pass from small scales to large. In fact, the energy transfer is still mostly from large scales to small. The rate of dissipation at these small scales is so great that as the turbulent field decays, it is the large-scale motions which are the last to die. Similarly, in cumulus clouds, one can differentiate between vigorously convecting clouds with their abundance of small-scale structure and those which have consumed most of their energy. It would be unwise to consider that in a turbulent flow, it is merely the Reynolds number which is of importance and that nothing else counts. In some cases, the Reynolds number may be enormous, many millions, and still no turbulence will exist because of the presence of some other influence, like rotation or density stratification, or, for conducting fluids, magnetic fields. Of these, buoyancy effects are the easiest understood. Here we have a water channel, which, partway, is divided by a horizontal partition. The flows are identical except for color. In this case, the two turbulent flows mingle fairly quickly and produce a single turbulent channel flow. Suppose we put hot water through the upper section and cold water through the lower. Buoyancy forces tend to resist the motion of fluid from the upper regions into the lower, and vice versa. The mixing achieved by the turbulence tends to make the fluid more homogeneous, and thus raises the center of gravity. In doing the work against buoyancy forces required to raise the center of gravity, the turbulence loses energy. Stable stratification of density, that is, light fluid above heavier fluid, thus acts to inhibit turbulence. On the other hand, if we invert the situation and put the light water through the lower channel and heavier water through the upper one, we greatly increase the turbulent activity. Let's look at that again. Stable. Unstable. In the atmosphere, both stable and unstable buoyancy effects occur frequently. Here, the air close to the ground is colder and heavier than the air above it. This stable situation is called an inversion by meteorologists. Vertical turbulent motions are strongly inhibited, and any motion which occurs tends to be almost purely horizontal. Smog can accumulate when an inversion at some height above a city prevents pollution from mixing upwards. On the other hand, it is not uncommon for the air close to the ground to be heated. This produces instability and vigorous convection. Convective effects also occur in some stars, including the sun. These cells are called granulations, although most of them are more than 1,000 kilometers in diameter. They are thought to indicate convective turbulence. Convective turbulence can easily be seen in a porridge pot. In our defining syndrome of turbulence, we did not use the word random, although it would seem to have been apropos. The reason that this word was avoided was because that, at least to some people, it carries with it the connotation of a Gaussian process. Turbulent distributions are more complicated than that. One of the ways of studying turbulent distributions is with a hot wire anemometer. The output of the hot wire is proportional to the airspeed. In this record, obtained in an atmospheric boundary layer, the large-scale motion is closely Gaussian, However, if we differentiate this signal, or if we examine any other property that is strongly dependent upon the small-scale motions, we find that the property seems to be distributed in concentrated bursts, separated by regions of comparative inactivity. A stationary Gaussian process could not behave in this way. There, the derivatives would look much like the original signal, except for a change in scale. The higher the Reynolds number of turbulence, the more marked this intermittency becomes, and it is particularly noticeable in geophysical flows. This record is of temperature fluctuations in the atmosphere, and this one of velocity fluctuations of a tidal flow in the ocean. As with many other aspects of turbulent behavior, we do not have a fully satisfactory theoretical explanation for this kind of intermittency. It is another manifestation of the baffling but fascinating complexity of turbulence.